Guys, this is Daniel Hayes again with video 2 for Lab 1. In this video we're going to talk about using the onboard switches to control the LED instead of just controlling it by software alone. So we can see in the manual here we've got two onboard switches, switch 1 and switch 2, and down here further in the manual we see that switch 1 and switch 2 are pins, so it's port F0 and port F4 are the two pins associated with the switches. So let's jump over to our code and see what we've got. So I've got a few more definitions here than I did last time, and we'll go through those as we need them, but we're just going to start off with our function prototypes and then the main function. So I've got my delay function defined here just like before. I've got a blink function, and now I've got a read switch function, and these are just my prototypes. All of them are not going to return anything. Delay, I'm just passing a float. Blink, I have a float, unsigned char, two of those, and then read switch, I got three unsigned chars. And the reason why I'm using unsigned char parameters is because they take up less space in memory. A char is only 8 bits maximum, so 255 maximum in decimal. So it uses less memory, and in most embedded systems you're constrained with memory. So I just went ahead and defined them as unsigned chars to minimize the amount of memory that this code uses. Main function, this line enables a clock. We went through that last time. These two lines we're going to skip for now, and we'll come back to them. And port FDIR, that's my definition of the direction register, and this register tells whether port F pins are inputs or outputs. Before I had just had a hex number here, I went ahead and defined that as a constant just to make it a little more clear on what this is doing. So set LEDs as output, and this is the same number as the other code. It's just I just gave it a name, and we got our 3 ones here, which enables as output the 3 LEDs. Now we don't need to change this number from the last code because our two switches are port F0 and port F4, but our switches are going to be inputs, and a 0 means an input, so we actually don't need to change anything from the last code. Next line, port FDIN, that is our digital enable register, pins to DIN. Again, I just named this before it was a number, and I just defined it to make it a little more understandable. So pins to digital enable, come up here to my definition, and we see it's 1F, and 1F in binary, skipping over the leading zeros because we're writing to a 32-bit register. So the first, let's see, 24 numbers are zeros, 24 bits are zeros, so I'm just omitted all those zeros, but they're there in the register. So what we're writing is 1F, and 1F is going to digital enable all our LEDs and our switches. Next line is enable pull-up resistors for switch 1 and switch 2. Okay, I have looked up in the manual for the pull-up resistor register, and that is right here. And we can see that from the manual on page 677, our offset is 510. And so what that means is, like I explained to another guy, is our base in the manual says for port F is 4002 5000, and that base address is like the street that we live on. So if we have the street, we have an idea of where we live, but we don't know where we live exactly. So when we add the offset to it, our offset is like the house number that we live at. So if you put the house number and the street number together, now you have the exact location of where you live. So the exact location of the pull-up resistor configuration register is our base plus our offset. So it's 4002 5510. That is our pull-up resistor configuration register. That's its exact address. So then we need something to write to that address to enable our pull-up resistors. And that's where I've defined set PUR, and I've used the number hex 11. And hex 11, as we can see right here, is going to put a 1 on PF4 and a 1 on PF0, which are our two switches. And we want pull-up resistors on them so we're not floating. By default, these they're kind of that's what it was. It was tri-state high impedance, so it's not exactly clear if it's a 1 or a 0 or a high low on those pins. So the pull-up resistor kind of just makes sure that it's either a 1 or a 0. So that's why we have to enable those. And that's what we're coming back here to the main code. So here's the address, and then this is the hex 11, which is going to enable our pull-up resistors for switch 1 and switch 2. Port F data, that's just initialized pin data to 0. Now we got a while 1, so forever we're going to read switch, and so this is switch 1, and then we're going to read switch 2, and then we're just going to keep looping and looping and looping until we figure out that, hey, one of these have been pushed. So what we're going to pass into the read switch function is 3 parameters. The first one is a shift, the second one is the mask, and then the third is which LED we want to blink. So if we jump down here to read switch, I've defined float seconds. That way I can do half a second or a quarter second, and I don't need to do whole number seconds. And then our number of flashes. And so down here we have if port F data and mask. All right, my mask is switch 1 mask in this case. So if we look up here on my definitions, switch 1 mask is to filter out all the data except the data on switch 1 pin. So we're going to, no matter what data is there, we're going to get rid of everything except the data on the pin of switch 1. And switch 1 is PF4, so that's bit 5. So if we look at our calculator, and so in binary, no hex, we want hex 10. In binary we can see that we got a 1 in PF4, so 0, 1, 2, 3, 4. So that's going to get rid of all the data except the data on switch 1. And that's the purpose of the mask. The shift is going to shift that data over into bit 1. Okay, the very first bit, which is technically bit 0, I guess, if you want to be technical. So we're going to, if we take our calculator, let's say we had, what was it, hex 10. So once we get rid of all the data except this bit right here, we need to shift it over to the first position so we can analyze it. So if we want to get this one over here, we go 1, 2, 3, 4. We got to shift it to the right 4 times. And that's what this S1 shift is for. Alright, so we're passing in our mask number and our shift number. So we're going to take the data, we're going to mask it so we get rid of everything but what we want. Then we're going to shift that data to the very first bit, and then we're going to compare it and see if it's active or not. Since we're using pull-up resistors, the switch is active low. So by default, when you're not pressing the switch, it will be a high on that pin, and then when you press it, it will be a 0. I guess you could do pull down resistors and it would be active high, but the way this is set up, it's active low. So we're looking for a 0. And if we have a 0, the switch is active, and then we're going to call our blink function. We're going to pass our seconds, our number of flashes, and our LED to flash. So coming up here to our blink function, I've got I defined, and I is just to determine how many times we're going to flash. And port F data, bitwise or LED, this turns on the LED. We're going to delay, then we're going to turn off the LED and delay, just like normal. And so that's basically how the code works. And once whatever happens, once we jump back to here again, we're just going to keep reading switch 1, switch 2, switch 1, switch 2, and see what kind of state they're in. For switch 2, it's PF0, and PF0 doesn't need a shift because it's already in the location that we want it to be, and the mask is hex 1 because it's in the first bit, which is PF0. That will get rid of all the data except for the data in bit 0. And we want it to blink blue if true. So switch 1 is red, switch 2 is blue. Now, I'm not using interrupts in this code. And so what that means is if I press the switch 1 and the red LED starts blinking, I cannot make the blue LED start blinking until the red one is complete. So I'll be stuck in this blink function until it completes and jumps back to the while 1 to start reading again. That's where interrupts come in handy. So an interrupt would be I'm in the middle of the blink function, but I can make it start blinking blue immediately when I pressed switch 2 because the interrupt controller will monitor any interrupts, and if it gets an interrupt, that process goes to the top of the list. It'll be high priority, and it will complete before anything else. So it will stop where it's doing. It will go to the interrupt controller. It'll process the interrupt sort of like a subroutine, and when it's complete, then it'll jump back to where it was before the interrupt occurred. I haven't got that configured yet. I'm going to start looking into it and see if I can get it to work, but I haven't done that yet. So for now, we have to wait for the LEDs to complete blinking before we can press another switch. So that's basically all of the code, except there's a couple other things I want to go over. And one is there's a special case for switch 2 that we have to look into. And what that is switch 2 by default has some kind of NMI configuration on it, so you can't actually use it as regular GPIO without first unlocking a commit register and then writing to the commit register the pin that you want to use as regular GPIO. I know it's kind of strange, but that's just the way the board was set up, is to use switch 2 as a regular GPIO, we have to unlock the commit register and then write to the commit register which pin we want to use. So if we go to the manual, actually on this line before we go to the manual is where the lock register is defined, and that's on page 684. So we'll jump over to the code here. I mean the manual, 684. And we can see that our offset is 520 from our base, 4002. 5000 is our base, 520 offset. So our address is 4002, 5520. And this is, again, is kind of strange, but it's what the manual says. That's all I know. To unlock the commit register, we have to write this number right here, 4C, 4F, 43, 4B, to the GPIO lock register. I don't know why. It just, that's the way I've got it set up. So you can see here I've got unlock GPIO, and there's that arbitrary number that they give in the manual. And that's, I didn't do any kind of special calculation here. It's just what they said to use. And again, this is just our location for our lock register. So coming back to the main code, we can see, okay, I've got my clock enabled, and then I'm going to unlock the commit register with that arbitrary number that the manual gave. And then here is our actual commit register right. So that CR is commit register. And if we come up here, we can see that we've defined the location according to the manual. Offset's 524. So 4002, 5524 is our location for this register. And what we're going to write to it is just hex 1, because the only pin that we need to basically get rid of this NMI default is switch 2, which is port PF0. And 0 is that very first bit. So we just need to write a 1 here. And all that does, these two lines right here, is just allows us to use switch 2 as a normal GPIO. And again, I don't know why they've got it by default to where you can't. It's just, that's the way it is. So with these two lines, we can now use switch 2 in our code. What else do I want to go over? One thing I do want to go over, because I don't think I hit it last video, was the port F data. And it's a little strange, but if we jump over to the manual, let's see, page 654. We can see in the example given that the actual address of the register, or whatever the address register we're using for data, is actually bits 2 through 9 instead of bits 0 through 7. Instead of 8 bits, we got to give it 10 bits, and I'm not sure exactly why it's set up this way. Again, I don't know why. It's just that's the way it's set up. So if we want to use the data from our LEDs and our two switches, that means we need to have, for our GPIO data, we need bits 0, 1, 2, 3, and 4. Because 1, 2, and 3 are LEDs, and 0 and 4 is our switches. So if you just look at those, that number in hex would be, let's see, 1 and then 1F. So in hex it would be 1F is the data that we want to use from the port F. But we don't write 1F, or we don't use 1F as the offset of this register. We have to tack on these two zeros to make it 2 through 9 bits. So instead of 1F, let's see, I think it's 7C, I think. So we got in hex, we got 1F, which is bits 0 through 4, which is our LEDs and our switches, and we're going to add we're going to add 2 zeros, and we can see in hex that's 7C. again, I don't know why it's set up this way, but we have to use bits 2 through 9 when we use this register. So we can see here that I've got my base plus 7C offset. And what this data register does, it just says that we're only going to be using these certain bits in the program. And that's the LEDs and the switches. So 1F in hex, bits 0 through 7, but we need bits 2 through 9, so we give 2 zeros, we add 2 zeros to it, which makes it 7C. I know that's strange, but it actually took me a few minutes to figure that out because my program didn't work at first, and I forgot that it was bits 2 through 9 because I was trying to use 1F the whole time. And then I finally realized where I messed up and added those 2 zeros, which turned 1F into 7C, and then all of it was good. The other thing I want to show you here, where I tripped up, was this line here. Was originally I had the mask and the shift in parentheses, and then I had a not sign in front of it, the little tilde thing. So like I had a not mask and shift data here, and then I had this equal to 1, and I never could get the LEDs to blink, and I just kept scratching my head, and I was like, what's going on here? Why is this not blinking? And it turns out what I didn't realize is that when I said not, this number in the end is still an 8-bit number. So when I said not 0, instead of just getting 1, I was actually getting 8 ones because it was an 8-bit number. So I was actually getting the number 255 and not 1. So I just like, oh, okay, well, I'll just get rid of the not and keep it 0. And I wrote a note to myself that it was active low. And that's why, just to remind me why it was equal to 0. And once I did that, it worked perfect. So that was the 2 snafus that I ran into in my code, but pretty much that's all there is to it. Like I said, I'd like to play with some of the interrupts later. I just hadn't gone around to it. And before I go, I will show you how this works. So we are going to build this and flash it, and then I'll turn on my webcam here. See if you can see the board here, and I'm going to hit switch 1, which the red LED should come on. And I think I've got my code to blink 5 times. And when it's done, I can push switch 2, and now I've got the blue LED blinking. And just to show you how the interrupts would work, so I'm going to hit switch 1, and I'm going to hit switch 2. And notice that my blue LED doesn't blink, and that's because my code has to finish before it can start reading switches again. And there you have it. Thanks for watching.